All right. Hi, everyone, and greetings from Northern Michigan. This is Bob, the science guy, and I'm joined today by Nathan. I guess we could call you globe hesitant. Would that be a good way of doing it?
I would say I'm definitively not a globe earther, and I think a flat Earth is much more likely than a globe Earth.
Okay. Well, one of the things that I kind of believe in is that if you're going to try and debunk a major paradigm that we have, such as the globe Earth, the heliocentric model, space travel, et cetera, I think that you really need to kind of have it, a basic understanding of what it is that you're debunking. Would you consider that fair?
I think that's fair. I think there are issues on both sides as far as complete understanding of the globe model, and I think it is useful to know a bit about it. A bit about it if you want to debunk it.
Okay. Now, just to make sure that we understand what this is a test that was put out by SciMan's not long ago. It's on approximately the 8th to 9th grade level, which here in the United States is 13 and 14-year-olds. Now, probably not your typical 13 to 14-year-old, but probably the type of 13 or 14-year-old that's going to go on to study algebra and geometry in high school. It's certainly not a college level or anything like that. The purpose of this is not to say, ha, 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 you don't know this, so you're a dummy, and therefore you're wrong. Many of us have not been in school. Many of us have not been in school for many years. We're adults, we're busy with our lives. And it may be 10, 15, 20 years or more since we were going to school, in high school. I don't expect you to know all of the answers. In all the years of training that I had, I never had a perfect score in any of my classes, of any significance. So we're all going to get things wrong once in a while. So the purpose is not just to show that you got an answer wrong. The purpose is to just kind of assess some general knowledge. Is that fair to you?
I think so, yeah. I did make a couple of points about the test before. I think that I could just say, we can trust the results of the test as much as we can trust the test itself. I guess I did bring up the fact that, kids of any age can memorize facts. It's not necessarily the same as having a deep understanding of the topic as a whole. But I haven't even seen the test, so I don't want to start criticizing it before I've even seen it. But yeah, I just had those couple of points to make, and yeah, let's see what it's like.
All right, there's a couple of notes that I would like to make on any test, and that is that any test can have poorly worded questions in it. Any test can rely more on memorization than understanding. The one thing that I will tell you from this test was, with one possible exception, you don't need to know any formulas. It's not something that you would have to study for in advance to memorize anything. This is just a basic understanding of the universe. And what we're doing is, the purpose of the test is not to debate the questions. This is not so much a test on, what I claim reality is. This is a test on your understanding of what the globe and the heliocentric theory and framework is. You don't have to necessarily agree with any of the answers to the test, but it's testing to see whether or not you understand what the common understanding of these things are. So let's go ahead and get going. Now, what I'm going to do is I'm going to share my screen. Can you see the test, and is it sufficient to you? Can you see it well enough? Now, I'm going to go over each of the questions, but I want to make sure that you can see the diagrams and everything. So the first question.
I can read the words, and yeah.
You can?
Yes.
Okay. So, there's going to be basically 10 questions in this test, and each question will have several parts. So the first question relates to this garden water feature, a little fountain. So we've got, as you can see, we've got a solar cell, we've got some wires going to a pump, which has a tube that goes up and puts water in this top jug, and then the water cascades back down. So, and here is the given. The solar cell absorbs energy from the sun. The solar cell is connected to a motor in the bowl. The motor drives a pump. The water is pumped up to the jug and then flows back down to the bowl. Now, using the above information, complete the following sentences using the words from this list. So,
Okay.
the words are
this doesn't seem too bad. I agree.
Yeah, words are chemical, electrical, gravitational potential, kinetic, light, sound, and thermal. The useful energy change in the solar cell is from light to what kind of energy?
I guess you could say electrical if you just want to say the solar cell itself.
Yep, well, that's the question. Okay, the useful energy change in the motor from electrical energy is to what kind of energy? And again, you've got your choices right there.
Well, so you could say kinetic or gravitational potential here, right? I mean,
well, you could, but only one would be right? You could say any of them, but there's only one right answer. What's your best guess? What's your best thought on it? Understanding that each one of those words has a different meaning.
Right, but I think both. Yeah, let me see if I can work out exactly what they're getting at, and I'll give an answer. Give me just a sec.
Sure.
If you say in the motor, I guess you could say kinetic. I think that's what they're getting at.
Okay, so I've got you down as kinetic. As the water flows from the jug to the bowl, blank energy is changed to what energy?
Okay. You mind showing me the diagram again so I can see which one is the jug and which one is the bowl?
Here's the jug right here.
So the jug.
And then here is the bowl. The bowl is the tub down below.
Okay. So we could go back down to the question again.
Now we're going to go back to the exact question. The water flows from the jug to the bowl. Blank energy is changed to what energy?
Here, I guess we could say gravitational energy is changed into kinetic energy.
So gravitational potential is changed to kinetic energy. Okay.
See, it is a bit, you could also say thermal energy. You could put some thermal energy in there, but I don't think that's
a lot of
what
different
they're
things.
getting at.
You could say a lot of different things, but we're going kind of for the best part of it. So air contains nitrogen. In the box, draw 5 circles to show the arrangement of the particles in nitrogen gas. How would you draw a gas with 5 particles in it? What are some features that you would want in the drawing?
If I'm allowed to ask this, are we just drawing a single N2 molecule? And so
no, we're drawing 5 N2 molecules, which are going to be formed as circles within the container, this box right here. How would they be arranged as a gas?
Are you sure that a single circle is representing an entire N2 molecule?
Yes. That's the way I'm stating it very clearly. In the box below, draw 5 circles to show the arrangement of particles in nitrogen gas. So a particle in nitrogen gas would be a nitrogen molecule. And that's the way I'm going to grade it. So how would those gas molecules be arranged in that box?
Okay. Okay, I don't entirely get what this is getting at. I guess they would just be arranged kind of randomly, roughly equally distributed, and they'd be moving with kind of random speeds and direction.
All right, so Xena carries a personal emergency alarm. It uses nitrogen gas to produce a very loud sound. And we can see the basic design of this alarm. It's got a lid on it, it's got a diaphragm, and it's got a cylinder with high pressure nitrogen gas. Now, the first question is, the nitrogen gas in the container is under much higher pressure than the nitrogen gas in the air. How does the arrangement of nitrogen particles change when the gas is under higher pressure? And they want just basically a couple of words on your part.
Okay. Right. So I think to sum up what I was saying before, to repeat some of what I was saying before, I guess that both temperature and the density of the gas might affect pressure, but in this case, it's probably the density. So I would just say that the particles are closer together. I guess you could say they have roughly the same speed as before. Their speed doesn't change, but you can't even really draw speed. So I'm not sure if that's part of that.
Okay.
So I guess there's not much I want to add.
The nitrogen in the container hitting the inside of the container is related to the nitrogen outside in the atmosphere hitting the outside of the container in what way?
I think I would choose greater than here.
Greater than.
Right. Because of
Okay.
the higher pressure.
All right. You ready for one of the more challenging ones?
Sure.
Xena pushes the lid down and the nitrogen gas escapes through the diaphragm. The diaphragm vibrates and produces a sound. The pattern on the oscilloscope screen below represents the sound wave produced by the alarm. So can you see the oscilloscope screen?
Yeah.
Okay. Part one, the loudness of the sound produced by the alarm decreases between point X and point Y. How can you tell that from this graph?
I guess well, you could say the amplitude. Maybe that's a good word for it. The amplitude of the wave is bigger at X and smaller at Y. It's like if this is a wave and it's going up and down, it's going up and down more at X than at Y.
All right.
So I would say if there's more, if it's changing more at X, there's more of a signal and it's louder.
The pitch of the sound produced by the alarm stays the same between X and Y. How can you tell this from the graph?
Okay, I guess that's because the pitch of sound is usually the frequency of the sound, and that's sort of the rate that the wave is going up and down, and you can see that stays pretty much the same. The rate in time being, I guess, because the horizontal axis is time.
All right, I'm not quite sure I understand what your answer is. Your first answer was the amplitude. Let me make sure I understand how you're using the term amplitude. What do you mean by amplitude?
You could say, well, as you see the wave going up and down, you could say the size of the peaks, like the distance between the top of the peak and the bottom of the peak.
Okay, and how does that contrast with frequency?
That would be kind of the size of the peaks in the horizontal way, because that's sort of representing time.
Very well. Okay. And you've answered both the questions there. Question number 3. In 2002, a large asteroid was discovered orbiting the sun, and its name was, I guess, Quasar. The diagram below shows Quasar in 4 positions in its orbit. So this ellipse is the orbit. That's point A, B, C, and D. And there is the sun. Question number 1. In which of the 4 positions, A, B, C, or D, is the effect of the sun's gravity greatest on Quasar? And explain your answer. So it's kind of a 2-part question. You have to give me a letter and you have to tell me why.
Okay. So assuming Newtonian gravity, I guess, or even maybe Einsteinian or whatever. And I guess by effect of the sun, they mean the force. I guess I would say C because C is closest to the sun.
Yeah, which of the 4 positions, A, B, C, or D, is the effect of the sun's gravity on Quasar the greatest? And your answer is C. And why is that?
Just pretty much because C is the point that's closest to the sun.
On the diagram, draw arrows to show the direction of the sun's gravity on Quasar in each of the positions A, B, and C. So how would you draw that? 3 o'clock.
I guess everywhere it's going to be pointed sort of toward the center of the sun.
All right, that's good enough for me. And
Okay.
I think you answered that question completely because you addressed all 4 positions. At which position, A, B, C, or D, is Quasar traveling the most slowly? And then why?
I guess that would be A. And you could say that's the point where it has the most potential energy. So it's lost all of its energy and motion. And so it's traveling the slowest there. Sure. Well, I guess it would just be more the farther away the 2 objects are.
You say that would be at A, and that's because that's the point of least potential energy, and there is the least potential energy when it's furthest from the sun. Would you agree?
I was saying A would have the most potential energy, and so the least kinetic energy. Okay.
Okay, so that's not what I heard. Okay, and that's your answer. Okay. You ready for the next one?
I think so.
Okay. See, this isn't all that bad, is it? I don't think this is an unfair test so far. The table
Yeah, so
below,
far it's not.
Yeah, I mean, there's not a lot.
Yeah, it's not too bad.
Yeah. The table below gives information about 3 of the planets in our solar system. Okay, we have the planet Saturn, Uranus, and Pluto. We have their average distance to the sun and the average time the time for one orbit in Earth years and the average surface temperature. Can you read those figures okay?
Yeah.
Okay. Now, the time for one orbit of the planet Neptune, which is not on the list, is 165 Earth years. Okay. Estimate the average distance of Neptune from the sun. Use the information in the table to help you. This is the most challenging question on the test.
Okay, I could see that. And as an overall comment, I do think that the test has been pretty fair. A couple of questions have been a little bit specific, or well, and it may be specific to the globe model. But I guess if this is a test about
on
the globe model, that could be that could be okay.
Okay, so what would the globe model say the answer to this test would be, or this question would be?
Right. So are we allowed to use a calculator for this?
Yes.
Okay.
If you wish.
Okay, sure. I'll give me just a second.
Take all the time you need.
Okay, I was double checking it. I didn't want to give a wrong answer. So I think about something like 4444. 4 digits. All 4s. 4. Is that million? Yeah. So I guess 4444 millions of kilometers.
Okay. And how did you come to that?
So I guess I went with Kepler's law. It's so I think it says the period of orbit should be proportional, I think, to the radius or the distance to the power of 3/2. And I think that's what I remembered at first, but I admit I Googled it quickly to double check, but it was the same thing that I remembered. So I didn't change my answer based on Google, but
well, you could have if you wanted to. But just tell me that you did it.
Okay.
How does the surface temperature of these planets vary with the distance to the sun?
That might also take a little bit of time. Yeah, so this is probably the hardest question.
Or is it? What's the biggest problem you run into testing, especially when you're testing for something designed for high schoolers?
I guess
that's the only hint that I'm going to give you. That's your one gimme. Let me read the question for you again. Answer the question that I ask you. All right.
Okay.
How does the surface temperature of these planets vary with distance from the sun?
I could just say it decreases.
It decreases with what?
It decreases with increasing distance, or so I guess they're, well, you can't say exactly how they're proportional, but yeah, but it decreases when you increase distance from the sun.
Okay, explain why the temperature varies with distance from the sun in this way.
Okay. I guess the part that I thought might be hard here is if you had to get more detailed with the numbers.
Did it ask you for the
but
number?
if I'm allowed to, it asks how the temperature varies with distance. So you could, if you want to be specific, you might say, oh, it goes as it's inversely proportional or linear or something like that. But that would be difficult. And
Okay, so what are you answering now?
Anyway. Okay. Yeah, I think that what this is getting at is the fact that as you go further, the power that's being emitted by the sun is spread out over a larger total surface area, and so you could so the intensity kind of goes as this 1/square law, and
Okay,
so you
it's
have less
1
sunlight
over the
at
square. It's the 1/square law. Are you aware that
with
there's
distance.
another name for that? Or are you just having trouble forcing your mouth to say it?
I guess inverse square law.
All right, so we're going to call
Yeah.
it the inverse square law, which is exactly what you said. All right, I haven't changed it at all. I'm just
Okay,
using a little
okay.
bit more standard nomenclature. Okay,
Okay. That works.
see, it's not a bad test. In the drawing below, you see an astronaut in a spacesuit. It has 4 small jets attached to his spacesuit, and these jets apply forces on the astronaut in the directions A, B, C, and D is the best wording for this question. So I'm going to modify it slightly. Do you agree? Are you all right with that?
Sure. I'm fine with that.
Okay. I'm going to say that that astronaut is neutrally buoyant, which means that if he was left alone, he would just sit there. Okay. So it's not like there's a force acting on him outside of these 4 jets. Do you understand what I'm getting at here? Like he's floating in a tank of water and he's neutrally buoyant. He's neither rising nor falling nor moving left or right.
Okay.
All motion of that astronaut is from those 4 jets. So the 4 jets produce forces on the astronaut in directions A, B, C, and D. A is to the top, B is his left, C downward, and D to his right. The drawing below shows the size and directions of the 4 forces acting on the astronaut. In what direction, A, B, C, or D, will the astronaut move? And I need a letter. So here we are. Now, according to this diagram, at point A, B, and D, the jets are producing 10 newtons. At point C, it is producing 9 newtons. And I need to know what direction A, B, C, or D the astronaut will move.
Okay. Yeah. Thank you. The clarification you gave at first was definitely helpful. That he's neutrally buoyant. Or just that he does not move at all, other than the effect of these 4 forces.
Yes.
Then in that case, he would move upwards. So I think that's A.
So A.
Right.
Oops. So you're going to say he's going to move upwards, A. All right. Now, in the next drawing, now, just to make sure that, okay. So rather than go back every time, A is up top, B is to the left, C is down, D is to the right. So in this case, at point D and point B, which is the astronaut's right and left, the jets are 10 newtons. At point A and C, which is the top and the bottom, it's 9 newtons. In what direction will the astronaut move and why?
Okay. Well, he wouldn't accelerate. So
What do you mean
could
by
say no direction, or
okay? So
say again.
So you say no direction, and why?
Right. I guess the four forces perfectly cancel each other out. The sort of the opposite direction arrows all cancel each other out.
Is there another name for that?
You could say the net force is 0.
Okay. So you've answered those two questions. Now, once again,
Okay.
we have our 4 jets. Jet A going upward is 12 newtons. Jet B going to his left is 12 newtons. Jet C going straight down is 9 newtons. And jet D going to his right is 9 newtons. Can you see it?
Yeah, it looks good.
Okay.
Yeah.
In what direction will the astronaut move and use the hands of the clock or use the hours of the clock?
Okay, right. So I think 3 o'clock. No, wait. 1:30.
1:30.
1:30. And I guess I could say that he would accelerate that direction, but
Towards 1:30.
Right. Which you could say is a little bit different from just plain motion, but yeah, I'll just say he accelerates in that direction.
Okay. Some pupils predict that water will evaporate faster if the surrounding air temperature is higher. To investigate their prediction, they place some water in containers in 2 different rooms. Give 2 factors they should keep the same in order to make their investigation fair.
Okay.
And again, this is open-ended. There are multiple answers that you could give here. As long as both your answers are correct, you get credit for it.
Okay, that helps. I guess one you could say the temperature of the water. Just with the way that they worded it here, if you really care about specifically how the surrounding air affects things, you could say you'd want to keep the temperature of the water the same.
The whole time?
Some other people, for both of them, yeah.
The whole time?
Actually, yeah, that would help too if you could. I guess you would have to somehow keep the water from coming to room temperature. But yeah, if you could do that, sure. I think that would help. Yeah. Actually, I think it might be necessary to specifically answer the question of how the surrounding air affects the evaporation.
Okay. And number 2?
That maybe you could say the amount of water and just the kind of container it's in, and just so it's
what specifically about the container?
Maybe the surface area would be important, or like how much of the water is touching the atmosphere.
Okay. Okay, they recorded the mass of the water and the container in room 1 and room 2 every day for 5 days. Then we have a little table right here. Explain why this is not sufficient to test their prediction. This requires a little thought. Let me reread it for you.
Okay.
Some people suggest, or some people predict, that water will evaporate faster if the surrounding air temperature is higher. To investigate their prediction, they place some water in containers in two different rooms. Give two factors that they should keep the same in order to make their investigation fair.
Right.
Now, you answered those two. They record the mass of the water and the container in room 1 and room 2 every day for 5 days. The table below shows their results. The data shown in their table is not sufficient to test their prediction. Explain why.
Okay. I guess it helps if they literally mean just the data in their table and nothing else.
It literally means just the data in the table and nothing else.
Right. Then I guess they don't give the temperature of the two rooms at any point in time, and they could even be changing over time. But yeah, so it could be that maybe room temperature is room 2 is the room 2 is the colder room. At least they don't yeah, they don't.
So that's your answer. They don't
there.
record the temperature. All right.
I think, yeah, I think that would be
All
one.
right. They plotted their data
issue.
for room 2 and attempted to draw a line of best fit. So they draw the mass of the water in container against the number of days. Describe the mistake they made in drawing a line of best fit.
Okay. Actually, mine is also in part B. They didn't mention like the temperature of the rooms in the question at all, did they? I'm just curious.
You mean in the proposal?
I don't think so. I guess, or yeah, just or anywhere. Yeah, it doesn't look like they really say whether room 1 is hotter or cooler. I just wanted to check if they had said that anywhere. But okay.
I didn't see it.
Okay.
Describe the mistake they made in drawing a line of best fit. I'm going to go ahead and blow that up for you a little bit. Can you see that a little better?
I can. I guess it's not really a line in a sense. Yeah, they shouldn't have connected each point together. That's I mean, that's I guess it just goes by what the definition of the line of best fit is, but usually that's like a straight line that would fit these points the best.
Okay. Now, using the data in the table, plot the points for room 1 and draw a line of best fit. With your permission, I'm going to go ahead and forego those two. I don't think that's necessary. I think you can plot lines or plot dots on a graph paper, and you did indicate that you had an answer for why this is not a line of best fit.
Okay.
Right. In which room did the water evaporate more quickly? And here's your table.
It looks like it's evaporating more quickly in room 2.
Okay, room 2. Very good. This thing is awesome. Until 1870 or until 1781, dyslexia cure for found, scientists thought there were only 6 planets in the solar system. Then a scientist called Herschel looked through a very large telescope that could turn to follow objects in space. He watched a bright object in the night sky for a few months and made drawings of what he saw. He concluded it was a planet, and there's his telescope. What method did Herschel use to discover the new planet? Tick the correct box. And your choices are: he carried out practical tests in the laboratory, he observed the environment, He asked other scientists' opinions, and he gathered data from the books.
I would say he observed the environment. That is a pretty cool looking
That's epic. The whole thing
construction.
rotates too, house and all.
Oh, wow. Okay.
All right. This is actually one of my favorite questions. The photographs show some pupils in a log car in a theme park ride. The drawing below shows the ride, and you have letters A, B, C, D, E, and F to show different points along the track. The car starts from point A, which is here, and travels to point F, where it stops by hitting a bumper. At E, the car enters a trench filled with water. At what 2 points does the car have no kinetic energy? At what 2 points does the car have no kinetic energy? And I need the letters. Can you see it okay?
Yeah. Well, F would be one of the points. Well, yeah, I mean F counts. Yeah, F would be one of the points.
It's got a letter to it, doesn't it?
Say that again.
It has a letter associated with it, does it not?
Right. No, I mean it would count as one of the points where it has no kinetic energy. Yeah.
So one of your answers is F.
Right,
What's the other answer?
Yeah, I guess I don't know if it doesn't really specify at A, I mean, whether it starts from rest or not. And other than that, it doesn't say where it stops either. So I'm not completely sure what.
The car starts from A and travels to F, where it stops by hitting a bumper. At point E, right here, the car enters a trench filled with water. So your choices are A, B, C, D, E, and F. You have already chosen F, unless you want to change your mind.
No, F is definitely good.
Okay.
If F isn't included in the answers, I would argue that F counts. But I guess if the car starting from A means it sort of starts from rest, then A would be a point. Otherwise, I don't think I can. Otherwise, I don't think you can say a second. I don't think you can give a second point from the information given.
Okay. At what point does the car have the most gravitational potential energy?
That would be A.
That's point A. You're doing great, man. At what point does the car have some kinetic energy and the least gravitational potential energy? Give the correct letter.
Well, also F, I guess. You could say E, but I think F would be more right than E. So I think I'm going to go with F.
You want to go with F?
Yeah.
All right. The cars are not powered by a motor. What forces the cars to move along the track from B to C? So from here to here.
In the globe model, it would be gravity.
This is a test of your knowledge of the globe model. When the car splashes through the water at E, it slows down. What force acts on the car to slow it down? Now, I'm going to have to interject on this one. There are many forces acting on the car. What is the main force responsible for the car slowing down? What causes that car to slow down?
Some kind of friction. I think whether, yeah, the friction could be made up of pressure or viscous forces, which I think I'm not sure. Not sure if I can answer.
Assume that the trench
yeah,
is filled
exactly how
with
the
water
friction-
because assume that the trench is filled with water because it says at point E, the car enters a trench filled with water. So it's not gelatin, okay?
Okay, right.
Okay. Complete the
Okay,
sentence.
so friction, I guess, yeah, I guess maybe you could say viscous or what, yeah, but I guess friction anyway. Sorry.
Okay, so you're going to say friction. Complete the sentence.
Right.
Complete the sentence below by choosing from the following words: chemical, gravitational potential, kinetic, light, sound, and thermal. When the car hits the bumper at F, it's what energy is transferred to what energy and what energy?
Well, I guess you could say it's kinetic energy for the first blank. Can you use a word more than once?
Well, no, it's looking for three separate words. Okay, when it hits F, and remember, that's the stop here. Okay.
Right. Although I thought it might bounce back at F, that it didn't stop completely, but it does stop momentarily. Anyway, yes. Okay. Yes.
Okay.
So okay, yeah. So I would say okay. So I guess kinetic for the first blank, and I guess you could say sound and thermal energy for the second two, if you wanted to use different words.
What's the thermal energy and the sound energy?
I guess the sound would be say again.
So how would sound and thermal energy be created with that?
So I guess the sound would be the sound of the impact itself.
Okay. And the thermal?
Right. I guess that would be energy of the impact kind of dissipated in the bumper. It should. I think it would actually heat up a little bit, and
okay,
you could say that.
The diagram below shows a ray of light hitting the surface of a mirror made of thick glass. The incident ray is both reflected and refracted, which means that it is, here's the incident ray. It comes out, or it hits the glass, and then it reflects. And then it also enters the glass and refracts. Now, I shouldn't have said that. Give the letters of the two reflected rays.
Okay, that's okay. Yeah, I guess yeah, A and C.
Are what?
For say for A and C would be the two reflected rays.
Okay. Give the letter of one refracted ray.
B could count.
The incident ray is brighter than ray A. Give one reason for this. The incident ray is brighter than ray A.
Right.
Here's the
you could say
ray, and there is ray A.
Right. You could say the energy in the incident ray has kind of been split up between rays A and B. And so each one will have less energy and be less bright. This has been sort of lucky for me because I guess it seems like it's mostly a physics test. And
Yeah, but I mean, it's
if it was
general,
other
it's
area,
general, yeah, it's general ninth grade knowledge of physics. Okay.
okay, yeah,
And you see that's not
yeah.
really formula heavy. This isn't a college level physics or earth science or chemistry or optics course. All right. Methane can be
Right.
a gas, a liquid, or a solid. In the diagram below, arrows P, Q, R, and S represent changes of state. So for example, right here, you have a change of state from liquid to gas along arrow P, okay? The boxes to the right show the arrangements of the particles of methane in each three physical state. Each circle represents an article or a particle of methane, okay? Draw a line from each physical state of methane to the arrangement of particles in that physical state. So which one of those represents the gas? Now we're talking about the boxes on the right. Which one of those is a gas?
That would be the bottom box.
And which one is a liquid?
That'd be the top box.
And of course, a solid.
The top, no, the middle box.
Okay. Now, arrows P, Q, R, and S represent a change of state. Which arrow represents evaporation?
I think that'd be P.
And which arrow represents melting?
That'd be R.
All right. Methane is the main compound in natural gas. The scale below shows the melting point and the boiling point of methane. So the melting point is negative 183 C. The boiling point is negative 162 C. Methane has three physical states: solid, liquid, and gas. What is the physical state of methane at negative 170?
Could be a liquid there.
Okay, the formula of methane is CH4. The symbol for the two elements in methane are C and H. Give the names of these two elements. Element C?
C is carbon and H is hydrogen.
Okay, got ahead of me there, man. When methane burns, it reacts with oxygen. One of the products is water, H2O. What is the other product?
That one, I'll have to think about. So you could say oxygen is O2. So you have a C, H4, and O2. So I guess I guess what's left over is carbon.
So just pure carbon?
I think it seems possible. It could just be, yeah, it seems like the only thing left over is carbon. I guess yeah, I'm not sure about the details. At least it would have carbon, uh, it would have carbon in it. If you have two oxygens, like say O2, then and you kind of add it to a single methane, I think you would get two two oxygen or two water molecules, and then just left over with a single carbon atom. I guess that'll be my guess.
Okay. Now our next one shows the orbits of Neptune, Pluto, and Earth. At 2 points, A and B, the orbit of Neptune and Pluto cross each other. Just kind of a cool thing, by the way. What force keeps the planets in orbit about the sun?
Gravity, since this is a test on the globe model. Yeah.
Give 2 reasons why it takes Pluto more time than Neptune to orbit the sun.
I'm not sure if this counts. You could say it has a longer distance to go, and it's probably
There are the orbits, by the way.
Thanks. Yeah. Yeah, that helps actually. Yeah. So I guess it has a longer distance to go, and it should also probably be traveling slower on average.
Okay, so it has a longer distance to go. And it's traveling slower. Is it driving or is it traveling?
Say that again.
Is it driving or is it traveling?
Oh, I guess it depends.
Depends if you're a sovereign
what jurisdiction it's under.
Yeah. Tom can see the sun because it is a light source. It gives out its own light. Pluto and Neptune are not light sources, but Tom can see them when he looks through his telescope. That must be one hell of a telescope because I can't even see Pluto. And I got a 10-inch Meade. At least I can't identify it. So explain why Tom can see Neptune and Pluto, even though they are not light sources.
You could say that the sunlight is reflecting off of them.
Now, I know that you're going to be very disappointed here, but this is the last question. Now, between point B and C, Pluto is nearer than Neptune to the Earth. Tom notices that Pluto is not as bright as Neptune, even when Pluto is closer than Neptune to the Earth. Give one reason why Pluto is not as bright as Neptune. And here are the orbits. So we're talking about this spot right here, where Pluto is closer than Neptune. So why, even when it's closer to the Earth, is it not as bright as Neptune? And there's a lot of different reasons. Just give me a valid one.
Okay. Did it ask for 2 reasons or sorry,
Nope.
or did I just
give one
figure that
reason?
wrong?
Give one reason why
Okay.
Pluto is not as bright as Neptune.
Okay. I think if I just go with the easy way out, I could just say it's smaller.